Hot damn, Dave Chesser.
Hello, hello.
Hello. Oh man, it was a private group, and I absolutely I'll just clear the air about it right off the bat. It was a small private group, and to distinguish between you and Dave Rossi, I may or may not have very respectfully referred to you as Mustache Dave before. You have a different action going on now. Just to get that out of the way right off the bat, man.
All good.
I'm grateful for your time, man. MIT studied UCLA for Yang Mills theory, dude. I'm super curious to get your input on some stuff if you wanna.
Definitely. Well, yeah, thanks for having me on, Evan. Good to talk to you.
Absolutely, Dave. No, it's good to talk to you too, man. I was I guess I'm gonna start off uh like traditionally, would you like for your research and stuff, would you say like the spin part would go like spin two or SU2 like is one of the more common ones out there. Would you wager or have a postulation maybe that like higher it would go higher for amounts or
Well, okay, so there's spin, right? So there's the Lorentz group, and that has representations for spin, like quantum spin for intrinsic quantum spin for elementary particles. Then there's like SU2, which does get used for spin, but it also gets used for the weak force. So I didn't know how to interpret your question. One way to interpret it would be to say, are there objects with higher spin? Potentially, right? So there's different elementary particles, and we know that the Higgs is a spin zero. We know that the electron and various other fermions are spin one half, which means they have two spin states. Like in chemistry, you'll have like an electron, two electrons can get paired together because they have two spin states. And then you can have spin one excitations, which have three states. And supersymmetry has proposed that there could be a spin three halves gravitino, but we have no experimental evidence of that. And then the graviton, technically, the graviton itself hasn't been detected per se, but it's very in line with gravitational waves. So we know that gravitational waves, if you treat it effectively as a field theory or, particle physics, essentially, then it becomes a spin two particle. And from there, you could hypothesize whether there's higher spin particles, and essentially, not at a naive level, those have been kind of ruled out for certain reasons. But there are some cases actually when you go to very high energies in gravity, effectively, when if you had like neutron stars that are overlapping and the matter is interacting with the matter and it's very gravitational, in those strong gravitational scenarios, it's helpful to approximate things in terms of an infinite number of higher spin states. So it's kind of remarkable that even if those things aren't physical, you can get tons of higher spin states that are useful for calculations. Then there's the other direction, which I don't know if that was exactly what you're asking, but you could say there's these things called Lie groups, and SU2 is an example of a Lie group. It's basically special unitary two by two complex matrices that allow for transformations to describe symmetries, continuous symmetries. And so there's different symmetry groups, and those have been classified more or less, at least the finite dimensional simple Lie groups. Those have been classified. And so there's SU3, there's SU4, SU5, and those actually get used in grand unified theories and unified field theories. So the idea is that these different Lie groups can be used to describe different forces in nature. So electromagnetism has a U1 symmetry. The electroweak force has an SU2 symmetry, actually SU2 cross U1 for the whole electroweak sector. And then QCD has SU3. And those get combined into the standard model. And then you could look at the Lorentz group for gravity. Obviously, quantizing gravity has its issues, but you could also play a game of trying to figure out, is there a single group that breaks into all those smaller groups, right? It's kind of like, is there one large group that contains all the pieces in it? And so that's another thing that I've been doing research on, particular with E8. There are ways to obtain the Lorentz group with the standard model. So yeah, two ways to interpret your question there.
Well, yeah, no, I guess the first your first description, I guess, was more along kind of what the lines I was thinking. Like if there was a, I don't know the right term. Like if there was a, if you could get like a spin two with would one of this, but it would be technically, I guess, two half spins and like a negative spin. If you could, does
Yeah, it's
that
a little
clock?
so there's two different quantum numbers for describing spin. One is kind of like the total spin, which just kind of sets almost like the floor for like the maximum spin it can have. And then the other one is like the actual spin state it has, which is kind of like what level you're at. So think of it as like an elevator, where like each elevator might only have two floors or five floors, right? But the different spin states that you're in would be like what level you're at on the elevator. Whereas like the particle type might say, oh, an electron only has two floors, right? So you could be at the lower floor or the top floor, right? But another particle might have a different elevator with like more floors, right? And then so then there's a couple things you can do. So you could bring particles together. Like you could make a composite, right? For instance, we know that protons are made of three quarks. So you can get to higher spin states by combining multiple spins and kind of studying them as a collective single object. But then there's some mathematics as well that describes kind of the spectrum. Basically, you can get a bigger elevator, right? But then, the levels that you might access realistically, there's also some mathematics involved there. So you can have like a negative spin state or a positive spin state as like levels in the elevator. Um, but yeah, you kind of have to just go through the details of the interactions for what's going on. I mean, you could have like two spin one half states can combine to give you like a spin zero state or a spin one state, but they're not going to give you like a spin two state. Uh, so yeah, like basically you can't make a really large elevator from two small elevators, right? Like if you brought two elevators together, then like you're only gonna be able to access so many floors, right? You need more elevators, more spin states, more particles or whatever. So I don't know if that helps.
Yeah. Oh no, it does. Well, because like the I kind of translate it to the condensate thing for like so if you're gonna have two photons just for example like you're gonna and you're trying to make a condensate like you're not gonna be able to do that with just throwing two photons in each other necessarily unless you got some other action going on there to the elevator point of like you could have a really deep elevator that goes way beyond whatever but if there's only one floor above ground you could it's only technically like a one floor elevator but in reality like whatever
Well,
negative.
yeah, and so then once you have like a macroscopic medium, then you have all of these spins that are around in a lattice, right? And so then those spins can point in different directions, which then it's typically a charge that's rotating, like an electron has a magnetic dipole moment or a proton. And so you can get these different spins that all have different orientations. And in certain scenarios, right, those spins could get aligned. And so you could have different phases of matter that describe how different spins get aligned, or maybe they get anti-aligned, or depending on what's going on. Like a permanent magnet, right? It's going to have a bunch of spins that are aligned, and that's what's giving it its magnetic field. It's the alignment of all the spins. And so, then there's other, you could have coherent states where like the spins are all coherent in a certain way and study exotic phases of matter as well. You get into that. So yeah, I mean you could think of it in a couple ways, I suppose. Like on the one hand, there's what's like a single object, right? Like are you thinking of a particle or a molecule or an atom, right? There you'd have the spin of that object, but then you could also have a bulk medium which has the interactions of all those spins, right? And then so that brings you in another landscape of what's possible.
Well, that's like you like the black hole, white hole territory of like energy density, like crazy way nothing that we're working with in the open here, right? Or
Well, I mean, I'm I don't see the exact relationship you're going for, but yeah, a black hole is basically an object that is so dense that even light can't escape it. So it's basically like the most attractive thing you could have in a sense where it sucks things in. And then the white hole is hypothesized as kind of being the opposite of that, right? Where so it would end up repelling a bunch of stuff. We're not really sure if white holes exist. I mean, it's sort of like a gravitational analog of like the difference between an electron and a positron, so to speak. You know, like an electron has negative charge, a positron is kind of the opposite and has positive charge. So there's some, notion of duality there, which I guess is similar to a notion of duality in black holes and white holes. But yeah.
But you know, to draw the analog in my mind anyway, it was like that would be like maybe a nature example of like needing crazy SU8 level like interaction of like the lattice of the whole like just of
Mm.
focus
Mm.
into one point. Maybe I'm mistaken. I that totally.
So no, it's interesting. There's a lot of stuff going on here. So when we're talking about these elementary interactions, like the standard model or electromagnetism or even gravity, the way there is an analogy between condensed matter systems and the quantum vacuum. Obviously, it's not as popular to refer to the ether, right? Now we call it the quantum vacuum, but we say the quantum vacuum gets polarized and electrodynamic media get polarized. The ether was a medium. So there's still some things where the quantum vacuum seems to encode interactions just like media kind of encode interactions. Now it's different, right? It's not just like a classical elastic medium. Now it's kind of this weird quantum fuzziness, right? But there's this notion in which you can kind of think of these different symmetry groups of the fundamental forces as being like different phases of the quantum vacuum itself. So when you take a crystal and you melt it, it turns into a liquid. And so now the atoms are all free to flow around. What you've done there is you've actually just lost a symmetry. You've broken a symmetry, right? Because with the crystal, you had this thing that had translation symmetry, right? Like let's just say you had a square lattice, right? So it's like a checkerboard pattern, right? Like if you go from one square to the other and you look around, like it all looks the same. It's all symmetric, right? Like if you're at one square or another, you're still surrounded by all squares, right? So it's symmetric in that sense. But when you melt that crystal, now you lose that symmetry. And so let's just say at very high energies, that the quantum vacuum entered a different phase of matter, or not even matter, just a different phase, such that different interactions could come out, right? Like one example is SU5. SU5 can break to the standard model. So it is possible that I mean, at very high energies, even higher energies than like what the LHC can probe right now, it is plausible that you could effectively model that as the quantum vacuum undergoing a phase transition. But if you're working with materials in the real world, you're not going to be able to really get to realistic energy, at least humans on the laboratories that we currently have in 2026, we're not going to have high enough energies to really cause a phase transition in the quantum vacuum, but we can cause phase transitions in media themselves, right? And so that's where honestly particle physics as a field is kind of dying, honestly, because there's not as many economical applications, and material science is very useful. So that's where most of the progress, condensed matter physics is referring to kind of condensed solids, solid state systems usually, sometimes liquids, but yeah, those are the types of systems where we're just having tons of discoveries about different exotic phases of matter. And there's so it's still using the same mathematical framework of quantum field theory, both for the particle physics and for condensed matter, right? Just as a table is made up of a bunch of atoms, a single atom is made up of protons and electrons and quarks. So there's some, and you can kind of follow through and do this thing called a tensor product that's going to give you the larger quantum Hilbert space that allows you to combine all those spin states, right, into one larger space. But so the mathematics is the same, but you know, the applications and kind of the manifestations of the math ends up being a little bit different. So things like SU8, I don't see as much in condensed matter, or like some of those continuous Lie groups. A lot of times it's more discrete symmetries because if you have, you know, like the vacuum is almost more continuous. In this analogy, if you're thinking of the quantum vacuum as like a lattice, then this lattice spacing would be like a Planck length or smaller. Like we don't know, right? So it's effectively zero, right? 10 to the minus what 34 meters or something like that. But we can't measure that anyways. So all of those Lie groups like SU2 and SU3 and SUN, those are usually for continuous symmetries. Like if I have a sphere or a circle and I rotate that circle infinitesimally, then it's still a circle. But if I took a square, I can only rotate it by 90 degrees to come back to a square. And that's because it's a discrete rotational symmetry. Like I can't rotate it infinitesimally, continuously. And so there's discrete symmetries and continuous symmetries. And so a lot of the stuff I did with the particle physics was usually dealing with the continuous symmetry groups.
So the discrete ones would be like the for a time crystal, like how it shifts. It goes dips below the Planck level of like whatever our like Hoffman, like we lose track of time at Planck, like basically that we
I
can't
mean,
measure.
yeah, I would start with discrete symmetries, just a simple lattice, right? Like a checkerboard, or just think of like you know, any crystal like NaCl, table salt. Like, you know, by the time we get salt, it's in these small granular crystals, but you can imagine there just being a huge salt crystal, like a single crystal, or zoom in, take a little grain, zoom in on it. All of the atoms are pretty much, you know, there can be defects and stuff as well, but they're going to be very much aligned. Like the bond angles are coming together in very specific geometries. And, you know, you have these discrete elements, right? There's individual atoms. So it's not like you can just you know, it's like imagine you just had an atom on each corner of a checkerboard, right? You're not like you could translate, you're going to have some translational symmetry, but only if you translate by a finite amount, by like the distance of that square, right? If you go from one square to another, it's the same lattice. But if you went the distance of like half of a square, then it's going to be like offset, right? So you don't have the continuous symmetry because you can't go halfway in between. You have to go in these like discrete, you know, you can go to one, two, three, four lattice sites over. It's kind of like a ladder, a discrete ladder.
Well, so to use that analogy and metaphor or whatever, like the newer stuff where they like crystallize light or whatever, that's where they take where it's in the discrete form and like shift it back towards like more base state or
Yeah, I don't know exactly what research you're referring to. I'd have to check it out.
oh shucks, yeah, I wish I
That
had that
sounds
handy.
like something that someone would have fun with a headline with for sure. Yeah, it can be hard reading scientific articles because a lot of times they just kind of have this crude headline that it's like sort of, you know, it's an analogy sort of, but it's like, is it actually that helpful? And then usually it's just written in a way that makes it sound super exciting when it's like not. I mean, you know, it's all interesting if you find it interesting, but yeah, I don't know. Like I'd have to see what they would did precisely.
Or it's like to your point, I
Maybe
think
they were
like
trapping light and making it very slow or something. I don't know. I'm just guessing.
oh, but yeah, I would have to. I wish I had that article handy, but to your point, I think like they also do it like oh, like the fine print at the bottom, like effect was one billionth of a second like long, like for in this special super condition, cold, whatever, like. But
Yeah. Yeah, that's the other thing. Sometimes you have these very exotic phenomena. It's like they occur, but only for a picosecond or whatever it is. So yeah, it's there for an instant.
I yeah,
Just good
I
to
don't
know.
I don't remember the exact. It was definitely somewhere. I think ResearchGate is where I saw it, but I'll send it to you after, but
No
it kind
worries.
of
Yeah.
reminds me of the base hit pyramid thing where like you're getting the photon to like kind of scoop up some other action somehow, like which I don't claim to know exactly, but like it's uh maybe that's like spin 2.5. I don't or I'm not sure like or a negative in there, but like to the scaling part of the crystal, like it must be like just like the regular light interaction, and then all of a sudden it's got some extra like waves going through it, and somehow I could show it to you, but or I think I could share. I have it ready to share, but I've showed it before on my stuff. It
Yeah,
I think
sometimes
it's. Oh, go ahead.
there are these in some of these condensed matter systems, what will happen is they'll shine light or maybe pump a material or do something optically, and then they'll get this effective quasi-particle that emerges in the system where it's almost like an electron plus a third of a photon or something like that. And you're like, what? Like, or it'll be something like, you have a magnetic field and there's, a fraction of a photon per lattice site, right? And then they'll say, okay, well, you have like a fraction of a photon and electron, let's say, but it's better to describe the system as having this emergent quasi-particle that is like both together, right? And then that thing has a bunch of weird properties. So I think that's probably one of the most exciting things happening in physics over the past 10, 20 years is just seeing how many different exotic quasi-particle phases that can be observed. So I don't know if that was an example of something like that. Maybe they were pumping light with something and then observing. It's because there are these things where you can get fractional spin statistics showing up in these condensed matter systems because typically, well, spin one half is already a fraction, but there are these quantum Hall effects and then fractional. There's the integer quantum Hall effect and the fractional quantum Hall effect, and both of those involve this kind of emergent quasi-particle story where you get this emergent quasi-particle that literally has like weird fractions of spin, like 2/3 or I don't know, 5/7 or what, like there's all these different ladders of weird spin states that you can reach where if you're in the quantum vacuum, you would never be able to reach those weird spin states. But in these materials, effectively, it's useful and a useful approximation to describe this system with these like really weird fractional spin states. So
Well, if you get it, and I thought I remembered on one of the podcasts you saying that you played music or were a fan, but like if you put it on like as a musician, like the timing of like oh every so many measures it's gonna lock in with itself. If you get that like that lock-in measure where it like stacks and you can just like bank that energy, do you think you could like amplify energy that way or
I mean, yeah, it depends on the details of the system. Maybe there's some rectification that it could occur if you're doing if you had some AC signal and you do something periodically, there might be a way to get that rectified into some DC signal, depending on the context. Uh, which I don't know, maybe there's some parametric amplification that could occur in some systems sort of like this. But yeah, it depends on the details ultimately. I don't know.
oh no no I appreciate it. Well, that kind of brings me to like where what do you the the firing order on like do you think or like even time space in general like what do you think the deal with that is if you care to dive into that like information wise or like it just total BS waste of time in your opinion or
Like space-time and
okay.
kind of like, well, yeah. So I mean, I suppose what's happening right now is even at the mainstream level, you have people like Nima or Connie Humed who's saying space-time is doomed. And so there's this kind of, along with space-time, it goes back to this idea of locality where things aren't action at a distance. Like things need to propagate locally. Like you can't just, spontaneously jump from here to there. Like something needs to propagate locally, right? And so that notion of locality is very much kind of ingrained in space-time. Honestly, at this point, the space-time is kind of like another kind of ether in a sense, right? It's like this, it's this pervasive medium, right? So people are starting to question, this is at the foundations of how we understand physics, right? Like we always observe things in space at a moment in time, right? Like the notion of an event, a point in space time is called an event. So, whether maybe it even is even difficult to think about what does it mean for time and space to be unified in a space time. Even putting that aside, right? It's still pretty intuitive to just we're recording events over time and space, right? Like that's kind of obvious to everyone, but maybe there's some more fundamental ledger, right? Maybe there's some more fundamental record keeping system that we don't understand yet. And there's some mathematical motivation for this with that Nima Arkani Hamed is seeing, where he's seeing this picture where locality and then unitarity, which kind of relates to probability conservation. Like the total probability should always sum to one. And that so locality and unitarity are two really foundational principles. You could say maybe locality is a little more relativity based and unitarity is a little bit more quantum mechanics based. So the idea is, if we've been stuck on quantizing gravity, so do we just keep trying of bashing, what we understand about quantum mechanics and what we understand about GR and just keep forcing them together? Or is there some new paradigm that we have to jump to where both of those things emerge out, right? And so that could involve going beyond space-time. So it's like maybe space-time isn't even fundamental. And then there's kind of the more esoteric traditions as well that might embrace these ideas with like less quantitative details that may or may not resonate, with other people. So there's kind of, it's easy to get into more mystical thinking and what that means. Is there an Akashic record? Is there, maybe the ether was meant to be this like mental realm, right? Or I don't know if you're into remote viewing, right? Like what's going on there. So, or what is consciousness, right? Like maybe really things are like this infinite dimensional conscious realm, and space time is emerging out of that. So I've been playing with some ideas lately. I haven't really published anything yet, but I've been looking at the quantum vacuum in a kind of different way, and it really goes back to some work that is in the literature from Garrett Lisi, who has this thing called the action reservoir. And what I'm starting to see is that all recorded information seems, for all interactions in the universe, they seem to get exported using this sort of, it's not a thermodynamic entropy, it's more of a quantum entropy. And it seems like all of quantum mechanics that we know of is kind of like in analogy with equilibrium thermodynamics. And I'm trying to figure out what is this picture for what space-time looks like when it becomes in these non-equilibrium states. So I'm still trying to piece together. There's a few different things I'm playing with. One of them is essentially melting space-time itself and looking at that mathematics. So right now, right, I was mentioning how space-time is kind of like an elastic medium, except very small. Like you could have atoms of space-time, except maybe they're on the Planck scale or smaller, right?
Smaller, probably.
Right. But then that's still it's very solid based, right? So it's kind of a crazy thought, but what if space-time, what if could you go to such high energies that space-time itself becomes fluidic in a way? Um, and or could it go beyond that? And right, like if it got beyond that where it was like a gas, like what what's that like if you could have little bubbles of space-time, like what are the voids behind those bubbles, right? So that's one direction, but then the other direction I've been looking at is just looking into kind of the quantum vacuum route. That was more of the gravity route, right? And then there's this quantum vacuum route where it seems like there are these I still need to do more research, but it seems like there are these infinite dimensional structures that are coming out of this view of the quantum vacuum, where essentially there's like this reservoir of action, which action is a physical quantity that is not very intuitive. There's this principle of least action, or really it should be called extremal action. So that's kind of an optimization technique that gets used to derive equations of motion. So you can specify the energy of things, like the potential energy, the kinetic energy, and you can have the Hamiltonian, which looks at the total energy, or you can have the Lagrangian that looks at the kinetic minus the potential. And then if you integrate that over time, that gives you the action. So, I mean, intuitively, action kind of usually actions require exerting energy over time, like just an intuitive human sense, right? So it's like, okay, I guess that makes sense. We're kind of integrating energy over time. Like that's a physical definition of action. And then basically, like systems always take the path that maximizes their action. So it's kind of like just like humans, I see a similarity between how humans behave in elementary particles in a vague sense, where it's like we're all given resources, right? And we're trying to like maximize what we can get out given the resources we have, right? And it just so happens that elementary particles don't have as many resources as human beings. Right? We have this brain, we have, motor control, we have senses, we can collect this data, we can like move things, we can eat. Elementary particles, they can follow their equations of motion. They have some quantum fluctuations, right? And so those quantum fluctuations are what I'm trying to hone in on, where historically it's been difficult to pin down what's been going on with those quantum fluctuations because we have this notion of quantum path integrals where it's almost like an interpretation of quantum mechanics is saying that a ball doesn't take one path, right? It takes all paths with different probabilities, which is kind of a metaphysical nightmare to even think about what that means, right? But there's still something going back to Einstein where it's like, God doesn't play dice. What if what if things were somehow more classical or more determined, right? Could you have a stochastic point of view where like what we know for sure is if you had an infinite number of identical experiments, an infinite number, and you ran all of them, then that ball would all across the infinite number of experiments, it would follow different paths, right? With different probabilities. That's what we know for sure. It doesn't mean that when we do one experiment that it's literally traveling all paths, right? Like we don't really know. Is it like is it traveling one path in one experiment, or is it traveling all with probability? I mean, even Schwinger, when he first introduced QED as a quantum field theory, he said, no, no, like you can't even, like, referring to the path isn't even a physical thing. All you can do is set it up and measurement. But it's, as a physicist, it was mathematically good, but, as a physicist, it's not very satisfactory because it's like, shut up. Nothing happens in between. You measure it, you start the experiment, then you measure it. Like nothing happens in between. And it's like, what? Like, no, I'm pretty sure something is happening in between there, right? So Feynman's view kind of pushed it in that direction where it's like, well, no, you can refer to these different paths, but it's still a little vague about what does that mean about kind of the ontology of reality, right? And so with this interpretation, I'm kind of taking Garrett Lisi's idea further and saying, what if there is this physical medium that has been overlooked that is a reservoir of quantum action that is analogous to a heat bath, where a heat bath, like if you just put I don't know, you put a rubber ducky in a bathtub, the bathtub is pretty warm, let's say, right? The rubber ducky's cold. Like thermal energy is gonna flow into the rubber ducky, right? And analogously, the fluctuations from your quantum fluctuations, I'm saying those are stemming from this action reservoir. And so it's kind of weird to think about action as a resource, right? Because we're thinking about it like integrating over time. Like it's a little easier to be like, I mean, I guess it's almost like the difference between going to the bank and like taking out a deposit versus like going through your life and you're just like slowly getting royalties like going into your bank account, right? Like it's kind of just happening continuously. It's kind of a weird thing to think about. But in that perspective, I'm trying to figure out now what is this action reservoir? Like, it's not, where is it? Where is it? It's not in space-time, right? It's, as far as I can tell, it seems beyond space-time. So right now I'm playing with the hypothesis that it might be some infinite dimensional realm associated with the quantum fields themselves. And so then if that's true, then there's this other, going back to kind of the space-time stuff I was talking about. There are ideas that, well, maybe space-time isn't even real, right? Like Einstein never said space-time was physical, right? Like ruler, like the whole point of space-time is really just it's like a frame of reference to talk about like what rulers and clocks would measure, right? You know, it's like the grid paper, like you draw a painting, but maybe you do it on graph paper, right? But the painting is what's physical. The graph paper is just the scaffolding for you to organize your thoughts, right? It's kind of like that, right? And so if you think about it, well, what is a ruler made of? Well, a ruler is made of matter, right? And then you could say, well, how do I measure the smallest things? With matter, right? Like anything you do, any measurement you make, it's gonna, I mean, and I'm using a very general definition of matter. I don't even mean, you know, you could be photons, it could even be light, or it could even be gravitational waves, I suppose. But, you know, it's gonna be some quantum field. You're gonna need stuff, right? Like you could have you know, a electron microscope. You're gonna fire electrons at something. The electrons are gonna bounce off, and they're gonna come back, and you're gonna say, "Aha! The electrons interacted in this way with this object, which means I getting spatial resolution. I can, you know, take that data and then reconstruct an image, right? And so our rulers, our measurement devices, they're made of matter, right? So what if space-time itself is actually constructed from these quantum fields, right? From matter itself. And so I'm hoping that this pursuit of the exotic differential geometry will kind of eventually connect to this other pursuit of looking into the quantum vacuum to try to say space-time is emerging out of this other abstract infinite dimensional realm, which then, you know, obviously this is super speculative, but I'm also curious whether that actually relates to consciousness or at least something similar to consciousness as well. So yeah, that's kind of a long-winded answer of kind of what I've been looking into towards going beyond space-time.
No, well, I dig it. Hey, no, that brings me to first, if it mass or whatever, I don't, it's a Bearden thing, but mass has like the time built into it. Like, it makes sense for action being like your whatever that the end of your equation. But if the ball's traveling along like as it goes, like whatever determines which potential it follows, like it dips into below the Planck scale and like picks up whatever like direction it needs. Is that kind of like and or uh time space as like an informational field where in really both the the examples maybe as and then your space-time emergent as
Yeah, so when you say time-space, you're distinguishing that from space-time?
yeah, yeah.
Okay. Yeah, I don't know what to think about that. I you know, I have thought about it. Some people refer to counter space, some people talk about time space. Um, yeah, there is some mathematics I'm looking at that is actually based on 4 plus 4 dimensions. And so I've been playing with this idea of, oh, could that be like space time plus time space? And what does that mean? Um, and it does turn out that this 4 plus 4 dimensional geometry is kind of the intermediary step to like melting space time. Like before, like it turns out that the stuff I need for melting space-time requires these infinite dimensional Lie groups. But to get so you have the Lorentz group, which is basically rotations and d equals 3 plus 1. So I suppose time space would be like d equals 1 plus 3, you know, And then so if you had space-time and some time space combined, that would be d equals 4 plus 4. And so I've been really fascinated actually with the differential geometry associated with 4 plus 4 dimensions. There's some unique properties of what's going on there. I mean, first of all, it relates to the split octonions, which is mathematically interesting. Second of all, it relates to Bott periodicity, which is curious. Third of all, it it combines the conformal group with non-metricity, which is probably technical. I don't, maybe I shouldn't even have said that because that's another can of worms. But yeah, basically the space-time geometry for like shearing stuff and stuff for conformal scaling with like angle preserving transformations, those get combined into this d equals 4 plus 4 rotational group. So basically, if you were to have some elastic solid and you want to start deforming it more, like maybe not quite literally melt it, but really start to deform it a lot, then you're going to get into some of these geometries. And so it's interesting because the conformal group has been sort of connected to mass, or really the lack of mass. Typically, when you have conformal symmetry, things are massless. So I've associated these three time dimensions with three generations of matter, which I've published some work on, and that's more conventional interpretation. So part of the issue, I've also like had some speculative thoughts on kind of the more mystical side of things, where it's like, what if kind of, as a conscious entity, there's like, the external world and then your internal modeling of that external world. And does that somehow relate to, like, could we somehow claim that as conscious beings, we're actually these infinite dimensional entities? And it's almost like there's gauge symmetries within gauge symmetries, or it's pretty abstract idea, but like basically at the end of the day, gravity or the symmetries of space-time are like the most external gauge symmetries. And it's like, can we start with infinite dimensions, go down this like Bott periodicity ladder, get to 8 dimensions, and kind of like think about this like internal versus external reflection, and then find like space-time emerging from that. I mean, it's super hand wavy. Honestly, like these aren't very rigorous statements by any means, but they're kind of ideas I've played with that have been in the back of my mind for about a decade, where it makes me wonder, right? Like, is there right, like from the conscious level, right? Like we all like to think that we have our own internal, I don't know, view of the world, which seems to make sense, right? Like obviously redness like isn't out there, right? Like it seems like we're having some qualia, some experience, right? And then that makes you wonder, so if like what makes us conscious, at the end of the day, maybe there's some notion of emergence, right? But it seems like an important ingredient is like having a body with neurons, right? Like, maybe we're a fancy computer, maybe we're a little more than a fancy computer, right? But it seems like matter is an important part of that, right? So it makes you wonder then, especially as we're building AI, right? Maybe they're not conscious like humans, but exhibit traits that could be argued to be conscious, right? Obviously, that's an ongoing debate. What do you mean by consciousness? But obviously, it's more within the realm of possibility than ever that within our lifetimes we might be able to have these computer systems that are conscious, right? So that makes you wonder, well, if everything is one or whatever, what does that even mean, right? I mean, at the end of the day, you have the freedom to describe the system however you want, right? Like you can say, no, 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 like this table is made of wood, right? And you're like, no, 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 this table is actually made of these atoms, right? And it's like, no, 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 it's made of these molecules. No, 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 it's made of these quarks, right? It doesn't really, each of those descriptions are valid. It's just each valid description is useful for simply characterizing certain things. So then it makes me think, well, what about the entire universe, right? Like if a human is conscious, if a computer is conscious, then the entire universe should be like the most conscious thing ever, right? And then so what is like the internal space of the entire universe, right? And is there kind of this internal external thing going on there? It makes me wonder. Obviously, this is a very human perspective, right? I might be anthropomorphizing the entire universe, so to speak, but it makes you wonder, right? Like, is there some internal realm to space-time that we're not, is space-time emergent? How does that work? Is there some mechanism, right? Is it just kind of this fairy dust land that doesn't make any sense, or is there actual some mathematical structure there where it's like, hey, no, like there's this deeper realm of reality that can be described with mathematics, and then space-time kind of condenses or emerges as like comes out of that, right? That's kind of how I'm framing it all. Yeah.
The Frank Wilczek shifting time crystal thing really like
Mm.
that slapped me from like the ju- the way that it's shaped first, and be like the functionality of it, and the to the you mentioned astral projection for a while ago, and uh again, I don't claim to be like friggin' whoever Captain Crow make a heavy hitter about anything, but like I've been doing it since 1997, and I wouldn't tell you what to believe, but I think that there's something to it personally there. Like the only example that I could use as like a real world analogy is coral, I guess, is you take it from its colony and put it anywhere around the world, and within a millisecond, like whenever it's time to shed, like all parts of it will shed like boop instantly, like regardless of location, which I think speaks to the larger information field, A, and B, like to like the maybe dipping, same thing as the time crystal, like dipping below the Planck threshold into like where we can't really measure yet, and then coming back to physicality, and or also to the universal point. Like personally, I'm right there, is or maybe right there, but like seems like the universe, like the body is physical, but like kind of our awareness. And again, I don't want to hand wavy consciousness bonkers land, but like our awareness definitely isn't in our meat suit per se. So I would just presume like the universe on a fractal scale would be just a larger version of that, like maybe beaming down to us, maybe not, or whatever. Like I would say also to that point, like the more we get a handle on it, like collectively, I feel like it definitely it helps spread the awareness also to kind of that point. But again,
Yeah,
can't
right. I mean,
not really test it.
I think it is interesting, right? You're talking about awareness, right? You say it feels to you like you've had some experiences where it's like out of your body, right? And I guess one of the things I'm worried about with science progressing so fast is that it's very easy to, as we become almost more materialistic, it's easier to keep our awareness in our body, and then it makes it, it's self-reinforcing when we come up with like new technological things and we see the power of it, right? And it's like, see, like this is working, right? And it's like, oh, and I haven't prayed in a while, and I haven't seen any miracles, right? And then it's like, well, you hear these claims of these miracles that occurred, but it's never happened to me, and I just keep my awareness in my body all the time. So like I never experienced any of these weird things, right? And then so it'd be very easy. I'm worried that humanity is going to get almost trapped in a materialist paradigm because it's going to be too difficult to scientifically probe these other things in comparison to what, it's just too easy to just build something and make money off of it, right? But right as I think it is kind of needed, in terms of we are reaching a weird point of, I would say, self-reflection in kind of humanity's history right now. I think we're really pushing up against the limits of our resources, right? Where we're starting to see, oh, like things are finite, right? We only have so much oil, we only have so much energy, and I don't think it's you don't want to just doom and gloom and be like, oh, everything's, we're just terrible and we're destroying the planet. But like, it is worth thinking about, right? And be like, okay, what do we do about that, right? And I think my hope is that if we can sort of eventually open up this kind of scientific realm of more spiritual ideas, it'll kind of make us rethink everything, right? It's like, oh, like we're more interconnected than we realize, and it'll kind of just recalibrate our values on everything, right? Like everything is so material based right now, and we're more connected than ever, yet still disconnected, right? Why is that, right? Like, and I think it really is because I think human nature, we all know deep down in us that there's like a part of us that is not almost spiritually getting expressed that should be. And it's like we're all repressed, but we don't have like the language to talk about it, or we're, afraid of getting laughed at, right? Or whatever it is, right? And so it's right. But like, I mean, even with consciousness research, I've seen a lot of progress in the past decade where, 15 years ago, it was pretty difficult to have any research on it. And now it's starting to get where there's maybe a few physicists on the planet who are like willing to dip their toes into it, right? Still, most physicists would be like, "Oh, I'm not going to touch consciousness." And really, that all started with like Galileo and Descartes back in those days, where it's like they recognized that, hey, we don't have the ability, we don't have the skill set to even evaluate what consciousness is. Like, it's better for us to separate our consciousness from experiments so we can isolate them, so we can get reproducible results. But we're kind of getting to a point where, it's we're reaching those limits. We're almost running out of experiments to do in certain aspects. I mean, yeah, there's certainly more material science. There's always more ways to combine pieces to make, bigger things. But I mean, with particle physics, that whole field's dying. I mean, with astrophysics, we're kind of just at the whim of what data comes in, you know? I mean, we can build better detectors and stuff like that, but like we figured out a lot. Like there's gravity, like we have the standard model. Yeah, sure, we don't know how quantum mechanics and gravity fits together, but there's not even the main issue is like there's not even experiments where quantum mechanics and gravity are both relevant. And that's the main reason why we haven't figured it out is because it's like for most of the experiments out there, we have a pretty decent description of them. So that once again is kind of it's showing us that we're ready. Humanity is ready to kind of tackle bigger problems, right? And I mean, consciousness is probably like the biggest problem to get to the bottom of scientifically. And I think that once that becomes more of a serious study and once we start having more breakthroughs in that, that's going to make us kind of rethink our whole social planet, right? How we interact, how we treat people, why we do the things we do, what our goals are, hopefully make things less competitive in a certain sense. Like it's like, oh, we're all on the same team. Or and then all the like UFO stuff. I mean, maybe that will lead to kind of humanity kind of embracing each other more, feeling like we're all on the same team, right? Um, as we start thinking about whether we want to leave the planet and, explore the solar system more, I think it is worthwhile to kind of get grounded on some almost spiritual, you know, same page of like, I don't know, it just seems like we keep messing
No,
up
I
and
agree.
dirtying
Totally.
everything and like, oh, we're destroying this planet, so let's leave, let's make sure we go to another planet. And it's like, well, why don't we like learn how to clean up planets first? And I think while our science is amazing, technology, I think the ultimate goal of technology is to free us. And on the other hand, we don't want to become too dependent on it. So it's a tricky balance, and I think we're in kind of one of the most fascinating times to be alive right now. But I suppose the now is always the most fascinating time, right? I suppose when the printing press was being invented, it was like, wow, like how could anyone ever say there's a better time to be alive, right? But they didn't know about AI or whatever, right? So,
Well, to the experiment point, and I actually reached out to Rupert Sheldrake and got past his initial person, and I haven't heard back from him. And I I have an idea, and maybe it's dumb, maybe it's not, but his anesthesia, the people watching you from behind are looking at you, and you can
Mm,
tell. I was thinking like just as like a experiment booster, or like maybe not, and it might be dumb, but like if you had a glass of water and the person watching you had a glass of water and or like just a balloon, you're holding a balloon like in any sort of like cluster of an element, I think your effect would go up but or like in terms of like you should be able to tell like it would be able to communicate data between the two aligned states or whatever if but it's consciousness stuff, so it's like stupid hard to it's stupid hard to throw stuff out there and be like I don't care if people laugh at me, but personally, but like there's like the flood of it from the AI thing of like, oh, you discovered whatever. Like everybody's got that pile of like pats on the back from the AI squad of stuff that
right.
which may or may not be guilty myself. I really try to limit it A and be aware of it B, but like the the part where the more of us I think are like where do you stand on the like do you think like there would be like we need like a spiritual wave to land over or like you're a deep like in order for folks to accept like and then again I haven't even asked if like where you stand on like Bedini or like Bearden or like Pudov stuff or whatever like if any of the outsider ideas or Stan Myers maybe like if we could develop that into like a legitimate thing and scale it.
Yeah. So, I mean, first to the spirituality stuff, I mean, I would say I think it's a little too optimistic to just assume that there's going to be like one prevailing thought, spiritual or religion or whatever that's just going to take over the globe. Um, but I think for me personally and just in my journey, I almost look at myself as kind of like a secret agent who's trying to what I don't really care what people believe. I just if there is sort of a mathematical aspect of let's say consciousness or spirituality, I guess I'm just worried that we're going to end up in a state where we're going to make it very difficult to actually detect these things. And I'm trying to just provide enough work to kind of maybe, I'm not even trying to convince scientists to be spiritual. It's more like here's some mathematics that exists and might apply to the world. What is the interpretation of that math, right? To me, it might relate to consciousness, but I don't really care how someone else interprets it, right? And honestly, it'd probably be better for a lot of people to not know my interpretation because that would be more off-putting to them, right? So, I mean, it depends, right? If I'm talking to you, I'll be very open about it, about my intentions because it's just the audience, right? Like different audiences need to get communicated to in different ways. And so I guess I want to provide work such that kind of a super hard-nosed skeptic materialist has at least some information that makes them be like a little more open-minded about what is the nature of reality. Like maybe we haven't got it all figured out, right? Like let's just say we enter a regime where we could go the next 1,000 years with never having a single quantum gravity experiment. Like what if we're in the same limbo forever, where it's like we do all the experiments, we sort of don't really have the full picture yet, but we can't really test anything more to figure out what that full picture is. I feel like it's very easy to just be like, well, that must be it then, right? And so it's tricky, but yeah, we'll see what happens. I mean, I think trying to really figure out what's going on with the quantum vacuum at a deeper level and what is going on with space time and how those two interlap. I mean, hopefully, like those ideas won't just die. I think physicists will still be passionate about that enough, and I think there is enough of thrust where maybe my worry and concern isn't actually a concern. But hey, that's just one of the things I've been focused on. Okay, and your second stuff was more about getting into different ideas, a lot of like free energy ideas or whatnot. Yeah, there's like Bedini, Bearden. I mean, with a lot of these, I suppose I was fascinated with them or inspired to see if there is something there. Keep an open mind about all of that. I mean, it's tricky because a lot of this information is just stuff on the internet, right? And so a, a lot of the claims that get made, or what Bearden would say, a lot of the technical details he would say are like wrong. Like it's very easy to just be like, "Oh, this is a bunch of garbage," right? But, it comes back to that whole thing I'm saying about communication where it's like you kind of have to figure out what did they intend to say rather than what did they say. Because maybe they didn't, it's clear that just because someone doesn't fully understand something, it doesn't mean they're wrong. But, if someone doesn't understand something, they probably have a higher probability of being wrong, right? So you do have to balance those things. But yeah, I mean, with my journey, what happened was I just took a bet where I figured I was studying quantum field theory. I was fascinated by the quantum vacuum. And I said, I bet within my lifetime, there's going to be some technological applications of this science that today seems absolutely crazy, just because that seems to always happen, right? Like 50 years later, some breakthrough happens where it's like no one saw it coming, right? And so I started doing internet research, like what might that look like? And, then I found people like Tom Bearden talking about essentially the quantum vacuum. And at first, it was just kind of a bunch of crazy claims about this and geopolitics, and I didn't really like want to get into that stuff. It was just like I just care about the physics, and it was like that's kind of weird. Like, why is he talking about all this other stuff? If he's trying to get this like physics message across, why is he talking about all this other crazy stuff? Because that's not really helping him. So that put me off to it for a while, and then yeah, like I eventually started collecting all these documents of like different people, like Stan Meyer, and it's like, oh, he got killed. Up, that guy got killed. Up, that guy got killed. So then like I had this document eventually where it's like I kind of had to just stop because I was like, what am I doing? Like I'm just making this laundry list of all these like researchers who have died, and I'm like, all right, so is this the direction I want to go into? Right? Like, what am I doing? And then so with Bearden and stuff, he would make all these claims. Like, oh, Maxwell's treatise actually had 20 equations. There's this missing term from Heaviside, this and that, and all this stuff. So it motivated me to go back to the original primary sources and read it for myself. So, because Bearden had collaborated with this was like AIAS group that I looked in some of their works. There's the Einstein-Cartan-Evans theory, and a lot of that was like kind of a bunch of nonsense. Like I don't know, it wasn't a complete theory. There was a lot of wishful thinking going on of people collaborating and then just kind of assume it's like, oh, you have your theory. Oh, I have my theory. Oh, yeah, like they must agree because we're friends and we're talking about the same thing. And it's like you kind of study the math and it's like, oh, they're kind of similar a little bit, but they're different. They don't really. And it's like, see, I have this theory and this theory, his theory fits in my theory, and it's like, no, they don't. So it seemed like a lot of wishful thinking and also there it seemed like there was some controversy of how they would even one of the co-authors, I don't know, I heard there was some drama about it's like did he even help the group that much? They just kind of put his name on it. Uh the was it JP Vigier? Vigier, Vigier. I don't know. So he was one of the co-authors and was kind of like, was he though? I heard from Jack Sarfati. I don't know. But basically, all that stuff, it was kind of like, I don't trust any of the specific details of what they're proposing, but what about the initial ideas, right? So, can I go back to the 1800s, read all that stuff? And I kind of found this picture that was kind of like Bearden should have been focusing more on extended electrodynamics for the things he was claiming with longitudinal modes and the Whittaker potentials. So I've been kind of studying that for 10, 15 years, um, developing kind of different classical theories of electrodynamics to kind of compare. And I don't know, at this point, I've kind of hit an interesting point in the past year with some of that research where Well, we're doing some experiments. We're working with some people that are doing some experiments, and so far the results are inconclusive, but I've more recently found something that might be more interesting that it's inspired by the mathematics of extended electrodynamics that might actually just apply to conventional macroscopic media. So I'm looking into that right now. But I mean, with the beer and stuff, it's hard to tell, right? Like, is there something there? I mean, at the end of the day, I think the most gracious thing you could say is, I mean, at the end of the day, you can have systems where the coefficients of performance is greater than one with like heat pumps and certain things. And so I think the big question is, can you have an electrical circuit that's solid state that somehow gets COP greater than one, such that you get quote unquote over unity where energy is still conserved, but you have to do something where you're putting in energy and it's somehow exploiting energy from the environment and getting energy out, right? And there's a few mechanisms that could be explored for how that could work. Um, I would say it seems like there are probably some systems where you can get very small amounts of power out. There are some systems, maybe it's not exactly what Bearden was had in mind. But for instance, like the work of Daniel Sheehan at UCSD or Paul Thibado, even there, you know, he published some scientific work and then had a patent, the patent claim to get power extraction. The scientific paper didn't really have enough experimental data to claim power extraction, but they talked about some specific metrics that almost, some specific measurements that almost implied they were getting power out, but they couldn't make it scientifically conclusive enough. So it's still can you essentially rectify thermal energy? It might be possible to turn that into electricity, but still, then the question becomes, A, how do you make it powerful? Like, how do you get a lot of energy out, and how do you make it affordable? That might be the next hurdle. And there's still even questions about whether it's doable. Yeah, I mean, and then there's like the Stanley Meyer stuff that all is kind of curious to me. I mean, I've seen a lot of YouTube videos of like, I don't know, people in third world countries with water power cars. I don't know. Are they hoaxes? I have no idea, but it seems like I've seen at least like a half dozen videos of people that seem to have something there. I don't know though. I have no idea. Um, yeah, I talked to Stephen Greer once about that. He claimed that he tried to get access to all the patents for the Stanley Meyer stuff, and then uh, someone else who was on the board of directors of that company that he was a part of got it and then didn't want to sell it or something. And then he claims that everyone else on the board was murdered, and then so that guy still has it. I don't know. I don't know if any of that information is true, but that was what I heard there. So. Yeah, I don't know. I don't know. I'm just trying to push forward on the fundamental science to really evaluate what's going on. Now I've been looking more into macroscopic media to try to see. It looks like there are certain diagnostic tools for evaluating how voltage and current, what's going on when you measure voltage and measure current. It's a little more complicated than that, right? Like you could have different systems with different charges coming in different ways, right? Like some systems could have charges tunneling, other systems could have free charge in a conductor, other systems could have bound charge in a dielectric. You could have like trap charge, you could have space. So different media would have different types of charge interactions. And so I've been looking into what happens when you have systems that have two or more different ways in which charge is flowing. And can you sort of I'm trying to just investigate whether there's subtle things that could be engineered that you couldn't really get access to by just measuring the total voltage or the total current. Um, so that's something I've been looking into. But yeah, I've been, I guess, naively open-minded towards the idea that maybe there's something possible that is novel in regards to energy. I've always found it strange that physicists have a fundamental like kickback to say there is no free energy, yet in undergraduate thermodynamics, there is literally a quantity called free energy. I don't know. So the free, I mean, so I just focus on thermodynamic free energy a lot because it's just a fun way to rigorously say the word free energy and not get in trouble for it. But essentially, we know that non-equilibrium systems have free energy, which means that the free energy is the amount of energy that can be extracted from the system as it approaches equilibrium. So we know that you can have a heat bath, right? Like you can have a hot and cold reservoir and you can do this whole thing, or you have air and a piston and you can make this heat engine that ends up basically, taking hot thermal energy, making it flow to the cold side, and you can extract a fraction of that energy as work. And that's just standard thermodynamics, right? But obviously the problem is making that a cyclic process, right? It would be great if you could just extract energy something for from something forever, right? But so you'd want to make something reversible because you want to come back to the same starting point so you can extract it again, right? Right? Obviously, you have a battery, but once the battery's dead, right? Okay, so you can recharge it, but that takes energy, right? So it's like, yeah, you can take charge from a battery, but how are you going to recharge it, right? That kind of thing. So, the holy grail would be a steady state solution that is different than the equilibrium state. All right, let me define what those things mean. So, because people define them differently. So, I define equilibrium as equal temperature, at least thermal equilibrium, as equal temperature. So, once things are at equilibrium, they tend to, not evolve further, right? They've reached their end point. But technically, the steady state solution is that endpoint. So the steady state solution is like, let's say you have a system, you wait an infinite amount of time. What is that state that you'll end up with? What is that steady state solution? Now, in equilibrium thermodynamics, it's just assumed that the steady state solution is the thermal equilibrium state. So some people might just define thermal equilibrium to mean that final steady state solution because they're almost assuming it has to be that, right? But what if it doesn't have to be that, right? I mean, just conceptually, what that would mean is you have a system that tends towards a non-equilibrium state. If that occurs, then it means there's thermodynamic free energy in that state. So, can I bring that state towards thermal equilibrium, extract a fraction of the work, and then, kind of disconnect the thing and let it go back towards that steady state solution? I mean, to a lot of physicists, it's like, oh, that has to be impossible, right? I don't know. I mean, it's kind of like the way I think about it is, and also with we know that like we don't have a great understanding of far from equilibrium thermodynamics. There is some advanced work on it, but for the most part, like undergraduate thermodynamics, classical thermodynamics is really thermodynamics near the equilibrium state. And so, yeah, if you study thermodynamics near equilibrium, like it's probably going to tend towards the equilibrium state, right? Like imagine a parabola, right? Like the ball is always going to roll down the hill towards the bottom, right? No matter even if you put it really high, it's going to roll down, right? And so we'll say, oh, like if there's a hill and there's a local minimum, let's just say it's a parabola, right? Because when we're nearby the local minimum, who cares about those higher order terms? All that matters is that quadratic term, right? And so it's almost like we've kind of made this. I'm if I have some hope towards exploiting this whole thermodynamic free energy, the hope is what if we're assuming everything is parabolas when it's not, right? Like what if there's a local minimum somewhere else far from equilibrium that's up here and the true equilibrium state's down here, And the key is to drive it so far away from equilibrium, it goes down on this other hill over here, right? And so the idea is it thermally it wants to go down here, but it can't because it would require too much energy or something like that, right? So it's like, is there some way to kind of exploit its tendency to want to go in this local minimum? Like, is that possible? That's kind of the intuitive picture I've had for, like 15 years, and I still don't really know if it is possible. I mean, I almost think it is possible. I mean, there's some thought experiments. I tried doing an experiment in grad school. It didn't really, it was ended up being inconclusive, but long story short, it does seem like there are some systems where you could play some games like this. I mean, there's like an example is why does it get cold on the top of a mountain? There's actually like not even a scientific consensus on this, which is hilarious to me. But if you go to the atmospheric scientists, they'll basically say adiabatic lapse rate with some technical term. It's basically just you get a temperature gradient due to gravity in a closed system at the end of the day. Like temperature is average kinetic energy of, gas molecules. So if you think about like just think of a tennis ball, right? Like if you throw a tennis ball up, because of gravity, it's going to reach some local maximum and then fall back down. And when it's at that local and when it's at that maximum height, it has zero velocity, right? So now let's just say you have a bunch of gas molecules, right? They're all going up and down. And so if you think about it, like, wouldn't there be more cold molecules at the top? Because when you throw them up, like they lose kinetic energy. So they get colder at the top. And it's actually like a it's a little difficult to think it through in your head. You kind of have to do the math, really, right? Because there's a few competing things. Well, the more obvious thing is, well, the pressure is going to be, higher at lower altitudes, right? Because, gravity's pushing it down. So like there's not going to be as many atoms up high, right? They're all going to be low. So that's kind of more obvious to figure out. Okay, so there's going to be a pressure difference, right? So then you can kind of rationalize it away and say, oh, well, what if, yeah, like on average, you throw the ball up and it's going to be, if you look at that one ball, it's going to have like, it's going to be colder at the top, but actually, you kind of have to look at the average of like, look at a unit volume and think about what's the average velocity of all of those things in there. And there was even a paper that tried to rationalize it away. But no, like if you do the math, it actually works out. You'll get a temperature gradient. And that's literally why it gets cold on the top of the mountain. It's kind of funny though, because like when you're in a room, heat rises, right? But that's actually because it's not thermally insulated. It depends on the boundary conditions. So the mathematics is saying if you had a perfect thermos, it actually gets colder on the top and hotter on the bottom. But if you open the door, the heat is going to rise. And so there's a vacuum around the entire Earth. So it's basically thermally isolated. It's complicated too because it's not, right? Because there's the sun, right? Which is obviously bringing in heat. And then also the ground is storing heat. But it turns out, let's just think about it this way. If you have a heat capacity of some object, which basically describes like how much energy is required to change its temperature. So if you take a really long tube and you thermally isolate it perfectly, just as it gets cold on the top of a mountain, it's going to get cold on the top of this tube and hot at the bottom. And then if you had another tube with a different heat capacity and you put them next to each other and you thermally connected them at the bottom, then they would be at the same temperature. But if they have different heat capacities, they're going to be at different temperatures at the top. And now they're at the same height. And so now can I turn that into a heat engine? Right? And so this was a thought experiment that was done in the 1800s by Loschmidt, and he brought it to Maxwell. And Maxwell, James Clerk Maxwell, like invented our understanding of Maxwell's equations of electrodynamics. So Maxwell said, I agree with all your mathematics, but it violates the second law, therefore it has to be impossible. I don't get it, but I don't think it'll work. And I don't know, I worked it through and it turns out it's not a perpetual mobile. It's both of them overlooked that eventually it just suck out all the heat from the thing. Like it's not, it doesn't last forever. It's actually just a really bad thermal battery that is really low power. Like maybe you could light up like I went through it. It's like if you had like a 10-story tall building that was perfectly thermally insulated, which is like how are you going to do that? Like maybe you could like get a like an LED bulb to like flash on like once a week. Maybe if you're lucky. I don't even know if you could do that. So it's like utterly useless, right? But that type of system is this type of system that's kind of exploiting things in a manner that I'm talking about, where a lot of these systems involve two dissimilar things close together that are connected such that they kind of have different biases in different ways, right? Like one might be like, this is kind of like thermodynamic and gravity, right? And then there's the material properties. So like maybe there could be another one that's like thermoelectric, right? So I'm trying to like analyze different macroscopic media, and it turn out it might not work, but I'm exploring that right now to try to see if there's ways to exploit systems to kind of basically shuffle energy around and get it to do things that you want.
Or to open, is it forbidden to say the or neg entropy or the open loop in the circles, or it's just
Well,
quackery?
so neg entropy was coined by Schrödinger, which is a physicist, and if you listen to what Schrödinger was eventually convinced that he shouldn't have used the term neg entropy, and it's actually just entropy. Um, so I personally don't love the term neg entropy. I think that a lot of this revolves around the idea of it being intuitive that entropy is supposed to like mix and disorganize things, whereas humans and life tend to organize things. So it seems like a paradox, as if life is violating the second law, but I don't think it does violate the second law. And so I think there was yeah, so there's this physicist named Brion, like it's French. I'm not pronouncing it great. Like Brillouin zones, or so he had a view on this that he kind of rebutted this Schrödinger, and his view was pretty accurate. But also I think there's something else going on with conscious systems with entropy that is different, and even things like time crystals kind of exhibit this behavior. It's kind of in between, where I think there's actually some forms of entropy that thermodynamic entropy is not taking into account yet. And so you have to look at the total entropy. And part of that entropy, I like to think of almost like game theory or like chess. Like if you think of a chess player, they try to keep their options in the future open, right? Like a good chess player, oftentimes you don't want to get cornered where you only have one move, right? Because obviously, like if you get cornered and like, oh, I can only move my king, and I can only move to this one spot and it's blocked, right? Checkmate, right? So it's good to keep your options open. And honestly, that's like one of the simplest algorithms you could think of, I think, to be like, how do I win at chess? It's just like keep your options open, right? Like if you have more moves to do, more likely you can like win, right? So like we do that with our thought. We do that by modeling the future, right? And we're modeling the future based on our memories of the past. And ideal gas molecules don't do that, right? Like they don't have memory, they don't have desires for the future. And so they're not thinking ahead, they're not trying to maximize their total entropy. They're trying to maximize their entropy in the moment. There's actually this paper um I, for, I forget if it's called entropic. I think it's called causal path entropy. I don't know. The paper introduces this notion of causal path entropy, which kind of extends this notion of entropic forces. And yeah, it's actually a really cool researcher who did that work. And they defined a type of entropy that is a path entropy, which is exactly relevant for like that chess player thing, right? Because it's not just about keeping your entropy maximized for the moment, it's also the future. And I think part of life, it's actually trying to maximize entropy. I kind of pitched it as like it's almost like the second law is transtemporal in a way. Like it's not just about maximizing entropy in the moment, it's a about maximizing total entropy. And I think uh there's forms of non-equilibrium thermodynamic entropy that have been introduced in the literature. And then there's some more kind of quantum information stuff, and then that causal path entropy. And I think all those things haven't been combined yet. So I think there's kind of like entropy in this direction and entropy in that direction has been explored, and no one has combined them to explore this other quadrant of like a more complicated form of entropy. And I think that life and complex systems are operating with that entropy. And so we don't have good intuition yet to fully see why we're actually increasing the entropy more than it might seem. And I think that also relates to the arrow of time because I almost think of it as like an entropy potential, right? Because there's this paradox of the arrow of the thermodynamic arrow of time where, and it kind of goes back to Boltzmann, where it seems like how did the universe start, right? Like it seemed like there was some event, like maybe the Big Bang was this statistical fluke of like some neg entropy event that had a really low probability event of happening, but it happened. But like entropy keeps increasing over time. So it's kind of like, how can it get so high? Like, how did it get so low in the first place? And I feel like we're just missing this notion about how complexity emerges over time. And there's almost like this entropy ceiling that's growing or this entropy potential or like as space-time expands it's almost like there's more entropy introduced in a sort of abstract, it doesn't literally increase the entropy in that moment but it's like gives you more room for entropy to increase. I'm still trying to figure out the best way to formulate it, but
Well, like if you put in negative mass for like the voids, what's it or like dark space, whatever you want to call it, would that straighten it out a little?
I don't see how right away. um yeah, I don't know. I mean, like there's like dark energy and stuff. Are you talking about that?
Yeah, yeah, or like yeah, or like not the like basically the flip or like cold electricity, like it would be the same thing, or like you get it maybe through
Yeah,
plasma.
I don't know what cold electricity is. I've heard a bunch of different people talk about it. I don't know if it's all the same thing. I don't even know what cold electricity is. I'm curious, figure out what's going on there. But yeah, I mean, so then there's dark energy, which I mean, honestly, I just kind of think of it as like a balloon expanding. It's almost like we're on the surface of a balloon and it's expanding. But yeah, it there is something that feels repulsive with it, right? So it makes one think if there's like negative mass involved because, oh, mass is positive and mass attracts, but it doesn't seem like it's actually a negative mass thing. I think one of the main reasons why is because the expansion of the universe, it's a different kind of repulsion than local interactions, right? It's not like, oh, my water and my coffee cup are getting locally repulsed. Like it's more like galaxies really far away are getting pushed away. Like it's a subtle weird thing, right? It's not like it doesn't seem as local of an interaction like other things in a way. If you get
Well, it would
like
be,
like
would
the
it be,
solar systems aren't spreading out, right? The solar systems are staying the same size, right? But the galaxies are spreading apart. So it's not like a scale transformation where everything at every scale is just repelling, right? It's really only on very large scales that things are repelling, and that makes it different than how like magnets repel. You know what I mean? So yeah, like there is something repulsive about dark energy, but even that language is a little sloppy, I would say, because it makes it too easy to make it think of like repulsive like magnets. But it's really that idea of yeah, so kind of think of like pennies on a balloon where a penny is a solar system or a galaxy, I should say. Like the penny itself isn't expanding, but the pennies are getting farther apart.
so like, like slow temporal decay? Like if you had like a water balloon and then you had like chunks of ice in there, like there, and you were kept filling it up, like there would be bits that were only going to expand so fast because they're frozen versus the rest of it is fluid-ish, or that's not a good example necessarily.
I mean, I almost see what you're going for. Um, well, yeah, so let's say you're filling up, it has ice in it, and then there's also water. Yeah, I don't know, like you could imagine it that like that, right? It's almost like a more 3D version. Let's just say these ice cubes didn't want to be next to each other. So they kind of randomly spread it out, and then you fill the balloon with water, and you just keep filling it up with water. It's like the ice just kind of spreads out, right? I don't know. You could think of it like that sort of.
And then our
Maybe not
universes would
literally
be
like a fluid, but yeah, sure.
our universes would be like the frost that comes out for the penny that you put on the ice, maybe.
Sorry, say that again. The
Like, and then like our universes would be like you put a penny on one of the ice cubes on the outside, and then like our universe would be like the physicality of like the frost that comes up onto the penny.
well,
Or
what I think is interesting is almost like okay, we have this notion of the visible universe, which is like the entire balloon, but then it's like, but wait, who's blowing the air in the balloon, right? Like, what's that about, right? So, um, who knows? I mean, I think the most satisfying answer to me would be there's must like, wouldn't it be beautiful if there's somehow some mechanism where like this quantum vacuum is somehow all related to the expansion of space-time and some like, some microcosm, macrocosm thing going on. I don't know. That would be a beautiful, but I don't know if it actually works that way, right? So it's like, right, like there's some notion of space-time expanding because space-time is literally getting created from the quantum vacuum. So like, does that mean this like maybe the balloon is embedded in this action reservoir, which is kind of like, I don't know, this quantum foam fairy dust realm. And then, space time is somehow emerging from that. I have no idea, but that's how I'd like to think of it. But, who knows? I gotta keep pushing with the math to see if some, like, usually what happens is I'll have this kind of intuition that's vague, and then I try to get math that is like vaguely within that realm. And then it's like, what does that math tell me precisely, right? Like the math might actually be like, it's sort of like that, but it's actually precisely like this. Sorry. And so that's kind of what I'm doing. It's like, let me try to get some vague intuition that's constraining enough, but freeing enough where I have some wiggle room to see if there's some self-consistent math within this framework. And then it's like, okay, what is that math telling me? So that's kind of how I'm trying to approach it, where it's yeah, I don't know why. Like it's been an idea that's been with humanity, like as above, so below, and kind of this whole like microcosm as the macrocosm idea. Like it's just why is that so attractive, right?
oh, I totally concur, man. Yeah, 1,000%. And like I appreciate the math aspect of it too. Like it makes me want to inquire if you think that there's still some uncharted map still to go out, like some numbers that people haven't put together yet, and or like phenomenology that maybe still needs sifting to a math format, like a new
I mean, I think honestly at this point we're gonna have to use our minds. I don't think it's gonna be experiments, right? And I think it's really about probing, yeah, what mathematics there is. Yeah, so some of the stuff I'm looking at right now relates to, I had mentioned the quantum field theory stuff, the quantum vacuum stuff, the action reservoir, and then I mentioned kind of melting space-time and going in that direction. So there's this thing called diffeomorphisms, which is kind of like almost like reparameterizations of space-time in a way, like coordinate transformations. And so, like you could do like Einstein's whole relativity thing kind of came from thinking about different observers and different reference frames, right? And so a reference frame has its own natural set of coordinates, right? And so, I mean, it gets to a point where, yeah, you could do like a Lorentz transformation and boost between two local reference frames, but you could even imagine crazier transformations that are completely nonlinear and just like more fluidic and all over the place. And so those types of transformations are the ones I'm looking into, which is getting into this infinite dimensional nonlinear diffeomorphism group. And so there's these other infinite dimensional groups associated with these Lie groups and kind of the representation theory for those Lie groups. There's kind of an infinite number of representations of a group, and I'm still piecing it all together, but it seems like there might be some infinite dimensional groups that end up connecting to both. And that's what I'm trying to find, like to kind of connect to this space-time geometry stuff and then also the kind of quantum vacuum stuff. So it's like looking into these like infinite dimensional algebras and trying to see if you can find a way where you can get space-time to emerge from these quantum fields in such a way that eventually, as it keeps emerging, you could sort of find these like natural reference systems that are like tuned to the structure of how space-time has emerged. And then that might, like, once that has kind of emerged enough, then it's like, okay, it's effectively like more solidified, right? And then it's like, once that's kind of cooled or solidified, right? And then it's like, that's where like the physics we know of with space-time might emerge. And like people talking about the Akashic record, right? Where it's like it feels more abstract of a space, right? Kind of like abstract mathematics, right? Like it's like, oh, you can think of whatever you want, and then it's like it just happens, but then it's not as like tangible, right? And I don't know, like it's hard to get intuition for like what would what would matter be. It's one thing to imagine a solid melting. Like that we can understand. But what if space-time itself melted, right? Like it's hard to get intuition for that, right? But I don't know, to me it sounds a lot like what this, these astral projections, right? Like it to me it seems like a good match where it's like yeah, you could kind of imagine everything. It's sort of fluidic or gaseous, flowing. It's kind of this flow state of thought, but it's not really tangible. Like everything keeps moving, right? Like it's not like you can pin it down. Like matter seems permanent. Spiritual seems transient or fleeting. This is something I've found paradoxical, which is like in some of the like new age, let's say late 1800s, 1900s traditions, it got this idea of like material and spiritual as being kind of polar opposites where the material is what's permanent and the spiritual is what is like instantaneous or flowing. And it was kind of pitched as like, oh, well, like, emotions are almost more spiritual. And it's kind of like you just get these, random floods of emotions right away. But it was also confusing to me because it's like, if you think of God as being kind of related to spirituality, like, isn't that more permanent than matter, right? So I've been kind of puzzled with this, right? And maybe that's sort of the resolution. It's like there's this larger realm that is, it's like kind of the Greek philosophical way. It might be saying, oh, like God is kind of related to the universe or the creator of the universe, who knows? Is that the same thing? Is that different thing? Right? But it's like there's this larger abstract realm, but then within that realm, you can't really get matter, right? Everything like the realm itself lasts forever, but everything in that realm is kind of more ephemeral. So I don't know. Is exploring that mathematics help us? Does that help us figure out how space-time emerges from consciousness? I mean, I hope so. Sounds cool, right?
Oh, absolutely. Hell yeah. It sounds super fun to me anyway. I'm here for it. And if the number part too, the more nailed down you get, man, I'm super amped to hear about it for sure.
And by what I mean by consciousness, I don't have to get too crazy, right? Like I let's just go the hard-nosed, skeptical, conservative, materialistic route, right? Like there's nothing special about me. I'm just a meat suit. I'm just a bunch of atoms. It's just a tensor product of a bunch of spins. Okay? But just as we can have a quantum field for a proton, we can have a quantum field for three quarks. We can combine three quarks and we can renormalize them and we can say, no, there's a better effective description. And that effective description, it's the same thing as the emergent quasi-particles. It's the same math. Like we don't really think of a proton as being an emergent quasi-particle, but it is. It's the same thing, right? Like it's just a new quantum field built out of pieces that is an effective description of what's going on. And so then let's take it a step further. Okay, great. Now we can have an atom. We can do that mathematically. We can say, all right, we have this Hilbert, this Fock space for the proton. We have an electron. So let's take a tensor product of those two. And now we have a hydrogen atom. Now we can have a quantum field for hydrogen atoms, right? Great. Now we can have molecules, right? We can do the same thing. Take a tensor product. We get a new emergent quantum field for a molecule, right? What about an organelle? What about an organ, right? I think there's a couple things that are going on here with why it's difficult to describe biology. Obviously, just the complexity of scale, right? Like it's hard enough to solve quantum mechanics for even a helium atom. It's kind of difficult. We can do the hydrogen atom in an undergraduate class. And there's certain approximations, there's tricks. We can do stuff with atoms, especially if it's like, an atom with one valence electron, then it's way easier because then you just pretend it's like, you have an atom with like 31 electrons, but let's just pretend those 30 electrons are grouped and then there's just one free electron. Like that's very easy to model. But even, a molecule, it's difficult for us to do all the rigorous quantum mechanics for that. So that's one difficulty. I think there's another difficulty of what is going on in complex systems where I also think there's going to be kind of like a unification of neural networks and renormalization in quantum field theory. Okay, what do I mean by that? So with neural networks, there's kind of these layers. There's there's like hidden layers of emergent complexity. So an example is there's a neural network in our eyes for detecting for vision for detecting things. So one of the first things that we do is we do edge detection. And so there's like a layer for edge detection that's like, okay, like do I see lines that are horizontal? Do I see lines that are vertical? Yes or no? And those features get fire when it sees that. And then those signals pass through and then it's kind of like, yeah, I don't know, everyone's brain's probably a little different, but let's just say the next level of features like, okay, like maybe it's like, are there triangles or squares, right? It's probably not literally that, right? But it would be something like that where there's different higher level features and it's like, okay, well, if there's edges, what do those edges make, right? And then it's like, then there would be higher level features. So just as like, a human is made up of different organs, which is made up of molecules, which is made up of atoms, right? Our vision of reality gets kind of broken down into these different hierarchies of features where it's like, you could edge detect. And I've literally seen this one time I like lost my vision for a bit and it was really cool. I saw the edge detection. I couldn't, so it was like I was at this rock concert and I was doing a fast and the music was so bad to me that it just like put me in the state where I just like went blind for like 5 minutes. It was really weird. And so I couldn't see anything for like a minute and a half. And my vision started coming back to me. And the first thing I could see was the edges. I saw it was black and I just started seeing these like white lines. And it was really cool because like I learned about this like oh, your eye has this. And And I literally like experienced it. And I was like, I could see like my neural network getting loaded back on. So I think what neural networks have that physicists currently don't have is the ability to kind of keep information at different scales, right? And kind of integrate it together. So what I mean by that is like once we have the proton, we say forget about the quarks, right? Everything's in terms of this proton now, right? And so I think one of the special things about at least human consciousness is our ability to kind of offload things to different scales, right? It's like kind of amazing that we can breathe without thinking about it, right? It's like that's a lower level thing, you know, our heart's doing its mechanical thing to pump, right? And then our whole body's consciousness is kind of like at a higher scale that's thinking. And so it's kind of like a neural network where it's like we can't just integrate out all the quarks, right? It's almost like we need, you know, once we're at the organ scale and going to the whole body, right? It's almost like we need some system to have quantum fields at different scales and to have those different quantum fields to have different goals. And a part of this notion of like emergence of consciousness, well, let's not even worry about consciousness. Let's just worry about actions that agents, conscious agents do. Like, what are things that we think are conscious, what do they do and what's their imprint on the physical world? What actions do they take that leave an imprint in physics, right? Like in matter, right? So it's like, hey, I use my consciousness to set a goal. I want to go on a walk today, so I'm going to go on this, you know, I'm going to go down this path versus that one, right? That's kind of how a conscious thing would is, you know, hey, I decided to go this direction rather than that direction, right? So once you have a physical system that has the ability to record information, that's kind of like the first step. Then it's like you have a system that becomes a non-ergodic system. That's actually what time crystals do. It allows you to, so there's a big assumption in thermodynamics, which is assuming you forget your initial conditions, you'll tend towards all final states with equal energy, with equal probability, right? And that's kind of this thing that's baked into the assumptions of quantum stat mech. But what if, you know, like I was saying, like I have a choice. I could go down this path or that path. Same energy, you know, the same altitude or whatever, same flatness. But, you know, I don't have to choose. I don't have to choose 50-50. I have the freedom to choose, go this way. Why do I get that freedom? I think the reason why I get that freedom is simply because I am a system that can record information in the first place. That's the first part of it. So the second part of it is being able to decide what information gets deleted or decide, like when you record information, you can filter it, right? Like you're not recording everything. To have some sort of ability to decide, you know, your own garbage collector, be like, okay, I recorded all these memories, but now, you know, now my memory's full. Let me keep the important memories, right? Well, what's important, right? Like as soon as you have a system that can make choices about deleting memories, I would say that's closer to being conscious, right? And I think those things are important, are almost prereqs for being able to model the future. To even get desires, right? I feel like having desires is kind of a conscious thing. Well, you know, really, you know, it's about qualia, having experiences, I suppose. But to me, it seems like conscious systems are trying to evolve their state through states of qualia, right? It's like you want to have the whole point of life is to have, it's not just to have these moments of experiences. It's about to, you know, have a movie, right? To have a story, to have a flow of through the experiences, right? You want the experiences to build towards something, right? And so that's about having desires, having a destiny, setting goals, right? And so, but if you don't have a memory of the past, it's the reflection of your memories that gives you the ability to model the future. And so you could, like, let's just say you have a complex system that's complex enough to record information, right? Like, is that conscious? You know, I don't know, probably like depends on your definition of consciousness, right? But like we now have physical systems, right? Like we have memory on a computer. it can record information, it can delete information, right? So you can imagine a system that is very close to a human being, that is just a meat suit of all these tensor products of spins. And I'm thinking about that organism as having a quantum field, and then all of its organs as having a quantum field, and then all of those organs having molecules, and those molecules have a quantum field. And so to me, I start thinking about that, and it makes me wonder if once we have that organism, that quantum field, it's an emergent, effective quantum field. And then we can ask the question, well, like, in what sense is that real, right? It's kind of just an effective description of all the pieces that are making it up, right? But what happens once the thing that I'm kind of currently caught on is what happens once you have your heart that's just trying to pump blood and your lungs that's just trying to breathe, and then you have your mind or your whole body or whatever that's trying to like get to work today, right? Like, how does that work where you have like these two different quantum fields at different scales that have different goals, right? Like, I don't know rigorously like how to really evolve those systems because quantum field theory doesn't really have that language yet, right? It's typically just, well, usually it's not even about setting goals. You just evolve the system, right? But I could sort of imagine where it's like you could play games where it's like you apply constraints, right? And those constraints to this physical system are like your desire manifold or whatever, right? Like, let's just say you had some system, but there's also another difficulty, right? Where it's like we have different desires on different scales, and getting the mathematical framework to deal with that, it seems like there will be some generalization of like neural networks with quantum field theory because the neural networks aren't really fully quantum, but they have this notion of back propagation of kind of like updating the weights at different levels, right? So like maybe there's some mechanism where it's like, oh, we see this and we observe this, and maybe like we're not even aware of it, but I don't know, like what if our lungs get recalibrated to like breathe better based on some other observation? I don't know, right? Or like, like I mean, it's probably true, right? Like there's probably things that you can do at a higher order level that lead to, just taking some supplement that lead to like your cells working better, right? Or I don't, right? Like things like that, where it's like you're making these decisions on a very high level order that's kind of like in the emergent quantum field realm that ends up making an impact at these lower levels for some other quantum fields, right? I think trying to figure out a framework on how to evolve those systems will help us piece that together. And then the thing that is very curious to me is to think about, well, if all of these things are created from these quantum fields, and then there is this human, the question and then becomes like, how far does emergence go? Can you have something that is greater than the pieces? And philosophically, there's a notion of weak emergence and strong emergence. And I have like a mathematical definition for that I haven't published. I probably should at some point, but to me, the weak emergence is simply the interactions of the pieces. So you could say, okay, like I have a bowling ball, right? How does the bowling ball work? Well, let's just smash it up into all its pieces and then study the pieces. Let's bring all the pieces really far away. Can we figure out how a bowling ball works from the pieces? Well, maybe, but also like you probably need to know how those pieces interact, right? And so obviously those interactions are something more. So that's kind of like a weak emergence, right? And so one hypothesis I have is that strong emergence is a kind of emergence that is when that emergent quantum field has structure that is not encoded in the pieces or its interactions. It's kind of like a fundamental realm. And so I could imagine like I don't know if there is God that gives entities free will. I don't like this could be the math for that, right? Because it's like how does free will emerge? I don't know. Maybe it is maybe the strong emergence doesn't exist, and maybe there's something where it's like
these quantum fluctuations, right? Maybe like quantum fluctuations are actually like a primitive amount of free will that everything has. Maybe an electron has an infinitesimal amount of free will, and there's some way where when you're doing these tensor products of all these spins to get macroscopic matter, maybe there's some way to cohere that free will. Like eventually you become this system that can do more than electron. Like that seems pretty clear. Like you can build a robot to do things that an electron can't do, right? So it's like it doesn't really have free will, but it can do things, right? And so there's kind of the capacity of what you can do, and then there's the choices you make within your capacity, right? So the capacity doesn't really seem like free will. The free will is like the ability to make that choice. But like maybe it turns out that all of matter has tons of free will, but just not capacity. And it's really like free will is the expression within the constraints of our capacity. I don't know. Or is free will some other thing that gets brought in? So this is like a hypothesis that I'm playing. I feel like it's actually like a scientific, like a rigorous hypothesis for like looking at this where you could say,
Mix of both. It could be a mix of both.
yeah, it could be a mix of both as well. Like, what if there's weak emergence and strong emergence? And so, the example, like just a silly toy model in my head, I call it is like the conscious proton. Like, what if there was an aspect of the proton that was not encoded in the interactions of the quarks alone? Like, what if there were some dynamics that you observed in the proton where it's like, oh, that's weird. Like, it seems to like mostly be described by the quark stuff, but there's this additional thing. And it's like, how do you pin down what that is? And the problem with this form of strong emergence, honestly, one of the main reasons I haven't published anything on it is because it almost starts poking holes at the scientific method because if you can't predict, like okay, you can combine things together and you could let's evolve the system, right? Like maybe you could say I understand the interactions, right? But if there's strong emergence, when you combine those things together, you don't even know what space will emerge, let alone what dynamics in that space will occur, right? Like to evolve a system through a space, you have to even know what the space is, right? Like, but if you don't even know what the space is, let alone what the stuff in the space is, it's like it seems like you're kind of doomed for trying to make a theory to predict what would occur, right? In other words, like how can a theory predict what you're going to think of tomorrow, right? Like if you're truly that creative and have so much free will, even if you understand how, like even if you had a supercomputer, right? That could be like, oh, the neurons in all your brain are this, like you're just a computer who went to bed and I analyzed all the neurons and I analyzed all your history. Like it's an open question. Is the evolution for how you act tomorrow, is that uniquely determined, or at least like maybe even probabilistically determined, or is there like some fundamental like just freedom that it's like, no, I get this ability to reprogram my brain, and I have the freedom to choose how I reprogram my brain, and then that freedom of choice allows me to do it, which then manifests it, and then it like redefines the whole quantum field of yourself. Like, do we have the ability to redefine the quantum field for our own identity? If we do, then
I
how
feel like
can you even predict
probably.
that?
Yeah.
And would that be a notion of strong emergence? And so at that point, it seems like it's even stronger than what Wolfram calls strong emergence. Like, because Wolfram's whole thing is like everything is a computation, right? Whereas Penrose is saying, well, what if consciousness is inherently like non-computational, right? So my notion of strong emergence would be kind of non-computational, where it's
Oh,
like,
speaking of free, could we pause just for 1 second? Just
for
so
sure.
my bad. I'm unprecedented pause. My
No,
bad
you're
on that one.
good.
No, I was gonna pick if you want to pick it up off the Penrose emergent consciousness thing, man. I definitely concur to the and or like any ideas like for where you could test it or whatever, because like I don't know if necessarily like math wise like would probably be your specialty to dig into where you could pin it down, but as a
Yeah, I
so
mean it's going to be a long time, but I thought more about just this notion of strong emergence. So it's kind of a crazy idea. Can you have a like a Hilbert space or a Fock space that just emerges fundamentally that is not predicted by any of the pieces? We've never observed anything that does this, but you could hypothesize, do humans do this, right? Um, and so then the question would be, well, how can you predict whether there is, how do you measure if there's strong emergence? The best thing I've thought about is I kind of have this little thought experiment. Imagine we went to another planet, we found this exoplanet, and it had a bunch of these rocks, they seemed like special rocks. We were like, let's call them conscious rocks. Like we weren't sure. It's like it seemed like there was some intelligence to these rocks, right? They kind of moved around or something. I don't know, like just some objects, and we're trying to evaluate like are these conscious or not. Um, do they have strong emergence in this definition that I have? The best thing I think you can do is basically take those rocks, smash them to a bunch of pieces, uh, discover what they're made of, then start studying how do all the pieces interact, right? And then just start modeling it and be like, okay, like we need to make a theory for how all these pieces work, how they all interact, right? And then you start reconstructing it closer and closer to what the original thing was, and see, does it behave like your modeling of it? So if eventually you got to something where it's like there's fundamentally no description that you can find, it's also like difficult. How do you know when you're done, right? Think of every possible theory possible and then test all of them. And then once you've exhausted that list, then you can say it has to be strongly emergent because we've tested everything. That's like there. I don't see any other way to model it. I can't think of any other way to deal with it unless there's some mechanism at which how the strong emergence is kind of introduced that describes that structure, which then you could claim maybe that's just hidden weak emergence, right? Like maybe like that was another thing I was thinking about is like is this notion of this notion of strong emergence could just be undiscovered weak emergence, right? It could be like hidden variables type of thing where it's like maybe there's actually secretly some hidden other data with some other hidden interactions that we're just not aware of, right? And there's almost like no way to really figure out like have I measured everything or not, right? I don't know, right? Like is there more there? Well, all you can use is what you have at your disposal. It's like, well, given the technology I have, it's not any of those things, but maybe it's something else we don't know about, right? So, um, and I think that's kind of the point. Like, life is so, I don't know, life is so mesmerizing that, like, to me, it seems to be the most interesting scenario that you could have systems that have strong emergence. Like, if I was an infinite creator and it would be possible to create these things, I feel like I would want to create them because you'd be curious to see what they do. And then anything else you create, you could just simulate anyway. So what's the point? I don't know, not to say that the universe needs a motivation to exist, but not to say that the universe requires some, intelligent design, but it I don't know, like I think humans are always mesmerized by how mysterious the universe is, and I don't think we're ever going to resolve. I don't think we're ever going to get to a point where we feel like we figured everything out. And so, we always I think we always will. I think we're never going to get to the bottom of this, right? Like, like people that are into all the ET stuff and believe it's real. It's like, oh yeah, they have all their sophisticated views on religion too. But even there, like they have access to these higher entities or whatever. Who knows if any of that's real? But it's like it doesn't seem like there's a claim that they've figured it all out either. You know what I mean? Like even if they are millions of years ahead of us, there's always going to be open questions, and I think there's going to be aspects of like consciousness we're never going to get to the bottom of, and I think part of the reason of that is because I think what would be most interesting is if fundamentally there's not a way to get a bottom of it, which means it's even more of an exciting adventure, right? It makes living even more exciting because, right? Like, I mean, with AI, it's kind of depressing, or it's like, oh, well, like, what's the point of life if AI is just going to take my job? I mean, to me, it's even more depressing if like everything is just a simulation, right? Like, it's like, what's the point? Like, like you can do other things behind besides having a job. Obviously, men kind of, almost define themselves by their job, but like, I think most people like to think there's more to life than just your job, right? But like,
Oh,
if
for
all
sure.
of life is just a simulation, then isn't that like more depressing than AI taking your job, right? Like, there's no like, where's the mystique? Where's the mystery? Where's the exploration, right? If it's all determined anyways, what's the point? And it's subtle because I should clarify there is this notion of probabilistically deterministic, or like just because you can simulate something, it doesn't mean it's uniquely determined, right? Like, with turbulent systems, you can't predict the outcome, right? Because small initial fluctuations can lead to large deviations in the output. And so there's still like mystery in that, where you could say, oh, well, we don't know how the game's going to play out. So it's still fun to play the game, even if it is simulated. People still have fun with video games, even if it is a simulation. But to me, it'd be even a more fun video game if like, imagine a video game with like, just completely unchained. It's like, the video game where you can rewrite the video game, like to me, that would be the most interesting reality to live in. Doesn't mean it's
Well,
real, but I hope it is.
well, what if it works like that? Like eventually, like you like enough people are like, oh shit, it's the video game now, and we can like respec our skill points now, and like that's like part of it is like just whatever awareness the universe is like. Oh, it'll be fun to see fucking Dave Chester use spent max out his flying points and like, oh, Evan's
Yeah, I
gonna
mean,
use his swimming ability. Like, look at that. They're having the bowling ball. Like, oh, to figure out what all these little fields are doing by themselves. So, oh, but I didn't mean to interrupt. Sorry.
no, you're good. I mean, I think that is, yeah, it's a funny thing, right? At the end of the day, like the goal of mental alchemy, I think, is to get to that point where it's almost like you're using your mind to almost hack the mental realm to then hack the physical realm, right? Like, can you use your mental capacities to immediately affect the physical? I mean, that's like the holy grail. That's like the philosopher's stone. But obviously, uh, it seems like we might have thousands of years before we get to that point, right? In the sense that, like, before you master mental alchemy, you have to master physical alchemy, which it's not even clear. We're still laughing at that if that's even possible, right? But I think there's this modern notion of like with these emergent of all these quasi particles. To me, I see that as a modern form of alchemy in the sense that, like, the ancient alchemy stuff. It's like, oh, can you turn lead into gold? I mean, yeah, that's cool, but to me, it's even more fascinating to be like, can you construct a new material effectively described of this new quasi particle that isn't even on the periodic table? To me, that's even more mind blowing than alchemy. Like, so at that point, it's not even about like, can you turn lead into gold? It's like, can you make whatever material you want with other properties you want by like inventing new quasi particles based on combining things? To me, that's fascinating, right? So then it's like, okay, taking that kind of going from physical alchemy to mental alchemy, right? So it's like once you understand how to control the physical things, then you have to like get into real. How can you control your mind, right? How can you? So we master how to manipulate the physical world. Then we have to master how to like get to know our mind. Then once we like master how to know what our mind is, it's like what is consciousness, right? Then like the first realm of like conscious technology would be like mental technology, which could be like, astral projection or remote viewing. right? It's like mental technology of like knowing how to use it to do things, right? And then at that point, then it's like once you unlock that, then it's like, can you use your mind to affect the physical world? But like obviously, that's the hardest thing to do. So at this point, most scientists would say that's impossible, right? Because it's like so far out of what we could imagine, right? And so, yeah, that would be kind of cool if we get to that point. There was some other point I was going to make circling around what you're saying, but I kind of forgot. But yeah, like it's kind of funny how there's that similarity between the mental realm and the physical realm, and kind of thinking of like, is there some structure to it? I don't know, like that's kind of what I find fascinating, but yeah.
Oh, for the video game aspect,
Oh, yeah,
definitely.
for the video game, right? Because then it's like, right? Because then once you unlock the mental alchemy affecting the physical world, that is like hacking the simulation, right? That is you rewriting the games of the video game, right? And then like I guess the idea would be maybe weak emergence would sort of be like, oh, there's like a finite number of ways you can hack it. That's almost like predetermined. Maybe that's sort of a way to think about it. Whereas strong emergence would be like, no, you can like just invent like new hacks fundamentally and then import those. I don't know, something sort of like that. So I suppose, yeah, even if there isn't strong emergence, there's still a lot of fun to be had. So I shouldn't get too depressed if none of that stuff is real. And yeah, that's the thing. Like I don't know if strong emergence is real at all. It could be fake, but what I found interesting is that it does seem like it could at least be mathematically defined. Now, I don't, it doesn't seem like it can be experimentally tested. And so that's really weird. Like I've never had come across something like that, an idea where like a mathematically well idea. I mean, there's probably tons of examples of people who have done stuff like this, but it's just weird where it's like almost like a physical theory that can't be tested, which sounds like a bad thing because it's like unfalsifiable. But what if the description of the universe turns out to not be like what if we can't test the nature of reality at a fundamental level? Like we might get to a point where it's like, yep, that's just the way it works. Like you just can't know everything, right? Like
Like there's the mystery section there that would piss off so many people, but I think it'd be fun still to find where that edge is.
yeah, exactly. And so I mean, I think we're always gonna push that barrier of that edge, and we're never gonna know. Like, have we reached the end of can we push it further? Or like it just fundamentally can't be pushed further. I don't think we're ever gonna figure that out.
I well, I think you're right first, and I think maybe it's like there's folks that are whatever invested for whatever reason. They're like planted their flag. They're like, this is the edge right here. Hey, don't look any further. Don't worry about that. Hey, over there. Hey, looks like there's more edge over there. Like, nope, don't worry about it. Well, boy, we're gonna keep checking out stuff anyway. Maybe there's more edge. Maybe there's not. Like,
Yeah. I mean, usually I think what people do is they really focus on their lifetime. So they end up confusing what is possible with what is possible within their lifetime, right? It's like, no, that'll never happen within my lifetime, right? It's like there's a big difference there, right? And so yeah, and I think it does give this natural tendency to, 30 years kind of like between every generation. So gives an opportunity for new ideas to get recycled in, right? Because when you have someone that's old, right, they've lived their whole life thinking, well, I already said that's not AGI's, if you're 80 years old, it's like, I'm still right. AGI is not going to happen by the time I'm alive, right? It's like, well, you could have that debate. Like maybe you are right. I don't know, right? And maybe it has happened, maybe it hasn't, right? But like if you're young, it's like, I don't know. I don't know. I don't think I can say that anymore, right? So, and yet the young and the old people are living at the same time. So like there's this constant turmoil from the younger generation thinking that more is possible. Part of it is because of the naivete, because they don't have that life experience of seeing everything go wrong. But the other part is because they're thinking further in the future. because they know they're going to live longer and they know that more things are going to get become possible in their lifetime than other people. And I think people overlook that a little bit.
Yeah, well, the acceleration too, like the just I assume you're kind of roughly, I'm not gonna ask how old or whatever, but like just going from Atari to Nintendo to AOL to today, like it's just that's a pretty steep gradient, which I'm stoked about. But if you're raised on like the just the last third of that, like and you project it forward, I see your point 100%, 150%.
Yeah. Yeah, and it's crazy how the technology affects how we communicate. Like, and communication is so important. I mean, for me, like I almost miss the AOL instant messenger days because it's like I don't know, it's just so easy to just talk and like you could type something out and take some time a little bit. It wasn't like an email, but you would actually like type out a sentence or two. Now everything's so text, it's so short, it's like hard to get meaning. I don't know. It was also probably the way I communicated too, but like I would kind of write things out in a little bit of detail and then like now it's almost this lost art where it's like maybe it's almost a little harder to talk to people in person sometimes. I mean, obviously you still can, but like everything's so digital, but it's like social media or text based that it's like and like, no one actually like has a conversation over email. Maybe to some degree some people do. Yeah, people have intellectual discussions and stuff, but I don't know, it's a little different where for me emails kind of just turn into like a boring work thing where it's like it's like checking the mail, right? Checking your email, right? So yeah, it is funny how like depending on your age and that it affects how you communicate and that affects your outlook on everything, how you communicate and like yeah, what is possible. Because I mean, communication is key for making progress. Like we need to communicate to build up further advancements. So like as things get easier to communicate, I mean, as AI gets introduced in things and you're gonna have all these micro transactions and bots doing this and that. Eventually, once there's like an entire economy running with all this communication happening in different ways, that's going to lead to another way, paradigm of things kind of occurring in new ways. And that's, like when we say what's possible, it's like, what do we mean? Like, how can we even conceive of what's going to be possible in 10,000 years? Like a million years? Like, there's just so many possibilities of what can occur. Like, yeah, I don't know. I think about the next 50 years, 150 years, 20 years, not much beyond that.
Yeah, like 20 years is like I feel like I'm slipping for an accurate guess, like for to take like the edgelord stuff that they have out now like in the open for that they're releasing for and then put it to like 1995. I wouldn't have guessed any part of it, no part of it correctly, like none. Like try to extrapolate forward and be like, that's well, you had like the Velcro part, like there's no more Velcro anymore now. It's all whatever. Like the rest of it was totally wrong. Like, damn it. Well,
Yeah.
hopefully more like ideally for me anyway, like divergence from dopamine, like screen addiction to like more nature and like awareness of like where your energy goes. But again, I'm not trying to jinx it, and I have no idea. Like it's just a hopeful guess anyway. But
Yeah, it is interesting to see, like, will we eventually kind of turn back and kind of re-embrace nature more, or will we just continue to get like more technological? Like, I hope it kind of gets integrated in some way, right? I think that would be cool.
do you think there was any resets before, like the like civilization resets for kind of along that lines of
Oh,
thought? Like we
I
got
mean,
we
I think certainly there's some resets of some kind. It's just a matter of how drastic they were, right? And how extreme, right? There's the whole what's his name? Graham Hancock, right? And I mean, I'm kind of fascinated by that stuff a little bit. I mean, it's kind of curious to wonder, when were the pyramids actually created? How are they built? That stuff. I mean, I don't think about it a lot really, but it's kind of a curious question for sure, right? And yeah, it's kind of an amusing thing where some people are like, no, it actually happened when what the Sphinx was like in alignment with Leo, and then other people are like, no, it actually is like 24,000 years before that on the previous cycle of zodiac. So I just think that's kind of a clever hypothesis. I just think it's kind of a funny thing where it's like, no, okay, it probably was pointing at the sky because they're trying to do this astrological alignment, but then it's like, well, it's like 26,000 years roughly. It's like, was it the last cycle or the one before that or one before that? And I don't know. I mean, the thing with the past is it's difficult to get that data, right? Like, how do you do an experiment? I mean, all you can do is really just analyze what's there and speculate. So it's hard to get to the bottom of the past, but I don't really know. I think that I think there's a combination of both things. I think there was more advancements in the past than we probably have realized, but it might not be as mind blowing as we think. And also just it is true that technology doesn't always advance linearly. Like it just goes off in random directions, random tangents. Like there could be some technology from the 1950s that like we don't understand as well as we did today, simply just because we don't make it anymore. Like the people who made it were the experts. Yeah, they documented some things, but they didn't literally write down everything they knew about it. And those people, like 50, 100 years go by, those people die or they're retired, and then that information gets lost. I mean, little things like, just stuff in NASA. Like I've heard little stories of like, oh, it's like, yeah, like we don't even know exactly how that thing works anymore. It's because like, there was so much energy and focus on going to the moon back then that now it's like, okay, we did that. Things get dormant. So it is possible you can get, I think there is some partial truth to the cyclic thing, but I don't know if it's as drastic as like, oh yeah, like we had, like there, I don't know, like I'm open to the idea that there was some spacefaring civilizations, like the stuff with the Piri-Reis map is curious, but I don't know if it's like, they were all like these master alchemists who were like, you know, joined with the gods or whatever. I don't, it's probably not that drastic, but who knows? I don't know.
Oh no, me
How
neither.
will we
No,
ever
it's
get to the bottom of it, right? Like,
right. No, or like if I mean if there was like that goes back to like the consciousness or the thing or like where your proof bar is, like if whatever you go down in the under the Sphinx and there's like a fucking vault with like holographic record of everyone, you'd get maybe you'd be like hey, or you or me would be like, hey, all right, that's cool, let's flip through and see what's up. But there would for sure be people would be like, that's total bullshit. And then on the other side of it, there would be people like, this is my new religion. Like,
yeah,
whereas
right.
we would be like, oh, that's interesting information to gather, like, or not, or it could be total bullshit. Like, I'm gonna look at it and maybe evaluate, but
Yeah. Yeah, I guess that's why I try to focus on things where I feel like there's some resolution where you can actually get to the bottom of it. Like even cosmology, like the concept that like you can't really do an experiment. It's kind of you're just like collecting data from the universe and just hoping it comes. It's kind of like archaeology. It's just like, well, let's just see what's in the sand. And then if it's there, it's there. But if it's not, it's not. Like, you can't really like control it in the same way. So it's difficult to. I mean, it's interesting, but how do you get to the bottom of it? I don't know.
yeah, that's super good question. Yeah, like the some sort of definitive baseline is usually good to have for a goalpost. I don't know that there would be one there, but interesting. Oh, I was gonna ask also if you had it's we're getting to almost the 3 hour mark. I was gonna ask if you had anything you wanted to plug or say or
I mean,
mention
not
up.
really. Yeah, I just put out a YouTube video for Kurt Mungel's contest. You can just search my name, David Chester. That was about that research paper I put out recently, looking into the teleparallel equivalence to general relativity, but it's kind of technical stuff, so probably not for everyone, but yeah, I mean, I'm not too self-promoting, but yeah, I don't know. Someone wants to reach out to me, that's cool, I guess. They can try to find me on whatever avenue they can find. I'll be cryptic about it. You got to work a little bit.
Oh, that's good. No, no, man. Yeah, the effort level, you gotta that goes to the action part. You don't just get the instant action. You gotta ramp up
Yeah.
to it.
Yeah. Well, my quantum gravity research email is broken, so maybe try to find another email if you're trying to email me. But yeah, I don't know. In general, if you reach out to me on Facebook or social media or whatever, usually I'll respond to people. But if you, I don't know, if you just like send me a message and actually say something, like if someone just like requests me, then I might not. But, or if they just say hi, I might just be like, hi. But I don't know, try to like say something interesting if you're going to reach out, I would say.
Or again, and I wouldn't presume to speak for you or anything, but occasionally it happens to me too. Or like, don't also not the 78, and I might have done this to you, hopefully not, but the 78-page AI manifesto of your sweet new original idea.
I mean, people can send me stuff. I just might not read it.
Right on. Hell yeah, hell yeah.
I think honestly, I don't read anything. I skim everything. So like with like physics and stuff. So usually I just open a document and just like look and just see what sticks. Usually I'm looking for math, but it depends. Or I'll just see what concepts they're talking, usually I just try to like pick it apart, like try to find some areas where it's like, wait a second, like usually I just start looking for errors, right? It's like, what's something that just looks absurd, right? And you just like pick it apart. You're like, oh, okay, I see what they're doing. They're saying this because of that. Or or just honestly trying to figure out what they're doing, right? Like if they're trying to you read the abstract and but yeah, that's the thing. I don't love reading, but it's a lot easier to write stuff now, right? There's some
It's what
technology for that.
get help writing stuff is a good way, also the good way to say it. Just like, but I just old school for like I have a paper like I prefer to write stuff like so like.
Oh yeah. But I mean, I use AI too. I've been using AI to write tons of stuff, so. But yeah, it's been a pleasure talking, Evan, and yeah, I appreciate you having me on.
Oh man, I was an absolute blast, dude. Sorry for the interruption, and if you're down, look forward to it. And I'm another one, because I was looking forward to this for a few weeks, dude, and I'm amped about how it went, dude. Beyond grateful for your time, sir.
Awesome. Well, thank you very much. Sweet.
Well, thank you so much for coming on, man. I'll just go ahead and hit the stop on the recording here.